well, old and young. I hope she will have a great introduction to time traveling simulators using blockchains and their applications, because that's what Justin's about to tell us. So, but due to the format of the panel, so if anyone who watched the video from the audience has a question, you can either ask questions on the Q&A, or if you can unmute yourself, you can just ask Justin. Otherwise, he would just give his small presentation. So if anyone has a question now, you can type in the chat or in the Q&A, and or just ask if you can unmute yourself. So Justin, let's just wait for 1 minute for people to type their questions. Otherwise, we can start. Okay, I don't see anything in the chat right now, so Justin, you can take it away.
Sounds good. Thanks for the introduction. I'll be talking about time traveling simulators using blockchains and their applications. This is a joint work with Vipul, Goyal, and Pratik, Soni. Blockchains are an emerging new technology with a variety of useful properties. So far, its primary application has been to enable decentralized currencies like Bitcoin and Ethereum. Just between these two, blockchain is trusted with securing a market cap of about $1 trillion. Historically, blockchains have often been viewed as a goal of cryptography, and there's been a lot of work on building blockchains using cryptography. Recently, they've also been viewed as an enabler for cryptography. Some recent works have shown that the properties of blockchain allow it to work as an alternative to a trusted setup to enable fairness in multi-party computation and more. In this work, we try to capture new security properties beyond the standard definitions, which allow a wider range of results while still being meaningful. In order to define our security notions, we need to quantify the knowledge that an adversary learned while interacting with the crypto system. Intuitively, whatever the adversary learns in a real interaction should be something they could learn on their own. So let's say that Alice knows a secret in some protocol, and we want to argue that the adversary does not learn anything about that secret at the end of the protocol. How we would formalize this is we would construct a simulator which can simulate the adversary's interaction with Alice without having access to Alice's secret. As a concrete example, let's think about a zero-knowledge proof, which we'll use as a running example through the rest of the presentation. In a zero-knowledge proof, the secret would be a witness to some NP statement. Then, since the simulator does not require the witness, the adversary can run it locally to learn whatever it would have learned in a real execution. And by definition, its interactions with the simulator can't reveal the witness. The simulation paradigm is extremely influential and is commonly considered the gold standard of cryptographic security for interactive protocols, since it's quite easy to define the exact behavior that you require. Philosophically, the simulator paradigm captures the idea that whatever a verifier learns from the proof, it could have learned on its own with just a bit of extra computation. Various relaxations of the standard definition modify this philosophy by allowing the simulator extra power. The resulting philosophy allows the verifier to learn whatever it would have anyway learned using that extra power. In this work, we propose a new philosophy. Anything the adversary learns now, it could have learned after waiting until tomorrow. We capture this idea by giving the simulator the ability to look into the future. Crucially, blockchains provide the notion of time, which allows us to exactly define this capability. Our primary contribution is our definition of time-traveling simulation, which I'll discuss in a minute. We also highlight the usefulness of our new notion by giving 3-round protocols for zero knowledge arguments and secure two-party computation. It's worth noting that 3-round zero-knowledge arguments with standard simulation are either impossible or so far require novel assumptions. And in the case of two-party computation, no 3-round construction is known with standard simulation that does not limit the power of one of the parties. Now let's discuss a little bit about exactly what time-traveling simulation is more exactly. To define the future, blockchains give a natural notion of time since the blocks are continually added. Additionally, it provides a predicate to check if a sequence of blocks is a valid extension of the current state. In other words, it's possible to check if a new state is actually from the future. And when parties begin the protocol, they're given the current state of the blockchain. As mentioned earlier, to quantify the security that this gives, we need to define a simulator which is not given the witness. And as a time-traveling simulator, it instead receives an extension of the current state of the blockchain by F blocks. This access to a future state is the core difference from the standard simulator definition. You can also define time-traveling simulators for other protocols, such as secure two-party computation, in a similar manner. It's very important that states too far into the future are hard for adversaries which control only a minority of computational power without waiting for that future to arrive naturally. In order to compute that future quickly, they'd have to mine blocks much faster than the honest parties, and that would violate the security of the blockchain. Now that we've defined time-traveling simulation, we need to answer how meaningful this new security notion is. Since we do give the simulator additional power as compared to a standard simulator, time-traveling zero-knowledge is technically weaker than standard zero-knowledge. However, the exact differences depend on the statement being proven. The weakness of time-traveling zero-knowledge appears when the statement being proven is inherently time-sensitive. For example, when proving knowledge of a solution to a time-lock puzzle, that puzzle will be solved by tomorrow. So a time-traveling zero-knowledge proof could leak the solution today. However, many statements that we care about are not actually time-sensitive. For example, a committed message will never be revealed until the committer decommits to it, no matter how much time passes in between. For these kinds of statements, time-traveling zero-knowledge is just as powerful as standard zero-knowledge. For more details, including a more detailed comparison of time-traveling simulation to other relaxed security notions, please see the whole versions of our talk or our paper. Thanks for listening.
Okay, thanks, Justin. Okay, so we have a couple more minutes. So if any of you have more questions to Justin, you can ask now. I'll be monitoring the chat and the Q&A just in case. Okay. I guess there are no more questions. So thanks, Justin. And I guess we'll go to the second talk right now. So now it's secret sharing, slice formulas, and monotone real circuits with Oded.
Thank you very much. Okay. So thanks. Hi, everyone. As mentioned, this is a talk about the secret sharing, slice formulas, and monotone real circuits, a joint work with Benny Applebaum, Amos Beimel, Naty Peter, and Tony Pitassi. And in this work, we studied 3 models. The first being secret sharing schemes, which is an information theoretic cryptographic model. And the other 2 are formulas or circuits that are enriched with special kinds of gates. So they will be either formulas over slice gates or circuits over monotone real gates. We'll define everything shortly. And we'll be interested in the connections between these three models, and we'll be able to gain benefits from all of them, where our goal will be new lower bounds for secret sharing. In the past couple of years, there have been major breakthroughs in secret sharing, and we would like to know if how much can these breakthroughs improve upper bound in secret sharing without introducing new ideas. And we show that there is a transformation from these secret sharing schemes, these new types, to formulas over slice gates, and from formulas over slice gates to circuits over real gates. And therefore we can take lower bounds that are already known for monotone real circuits and lift them to our model. And in the other direction, we can show that these upper bounds also apply to the circuit and formula models. And now we'll start by defining the three models and see why it's all interesting. So in a secret sharing scheme, we're given a list of authorized and unauthorized coalitions from a set of n parties. And a dealer wishes to distribute a single bit secret to all of the parties in a way such that it sends one message to each party. And we wish that every authorized coalitions from the list will be able to recover the secret from the shares it received, and that any unauthorized coalition will learn nothing information theoretically on the secret. And our goal will be to realize such an access structure, a list of authorized and unauthorized coalitions with minimal total share size. That will be our measure of complexity for this model. And it's a major open problem in information theoretic cryptography. What is the best achievable share size for the worst case function or access structure? And the first ones to consider this problem for general functions were Ito and Ali in 1987, and they showed a really high upper bound of 2 to the n, which is it seemed for 30 years that maybe this is by Liu, Vaikutanta, and we in 2018, they show that this can actually be improved, and since then the line of work improved this total share size for the worst case function to 2 to the 0.585 n. But the thing is that the lower bound for secret sharing is still really far below. It's not even quadratic. So a natural question to ask is how much further can these recent techniques improve secret sharing schemes? Can we get to sub-exponential complexity or even polynomial complexity? And we answer this question, and the answer is no. And we show that there exists a function in monotone NP such that these recent techniques can only get us to 2 to the n over log squared n, and not below that. So that's the state of affair for secret sharing schemes. And now we'll define the second model of formula over slice gates. So it's basically a formula where each gate can compute a slice function. So a slice function is a function that can take arbitrary values for inputs of a specific Hamming weight, let's say of Hamming weight k, but it must take the value 0 for lighter inputs and the value 1 for heavier inputs. So formally, it is a KL slice, has L input bits. It's unconstrained for inputs of size of Hamming weight k, 1 above and 0 below. And the formula over slices is a formula where each gate computes some KL slice function, but the weight k and the fun in L can vary between these different gates. And they are allowed to be arbitrarily large. So this seems like a very strong model. Nothing, it was shown in the work by LV, the first improvement to the secret sharing schemes, that their work was actually based on formulas over slices. But if you didn't know that, then the best possible upper bound would have been 2 to the n, since slices can also implement AND or OR gates. So we know that's the basic result. We know nothing about lower bounds prior to our work. And we'd expect this model to be very strong, since there are a lot of different such slice gates that can be incorporated to a circuit. So this number 2 to the n, choose n over 2, is just the number of slice gates with n input bits and slice parameter n over 2. So this is it for formulas over slices. And now the third model, which is formulas or circuits with a different kinds of special gates, will have monotone real gates. And these gates are completely different. They only have 2 input bits, but they can manipulate real numbers. So each such gate can take as input 2 real numbers, and it outputs a real number, but it is limited by a monotonicity. We will only work with monotone gates, where if we increase the inputs, the 2 inputs of the gate, then its output also must be increased. So if everything is real, then how does it have anything to do with Boolean circuits? Then we say that if a circuit has only binary inputs and outputs, then such a circuit will compute a Boolean function, but it is allowed to have real numbers that go through intermediate wires. This model was originated by Pudlak in '97, thinking of proof complexity. And since this is an old model, nothing was known for upper bounds, but there were lower bounds. So we know that monotone real circuit, there is a function which requires a circuit of size 2 to the omega of n to the third, and a formula of 2 to the omega of n over log squared n. So we would like to use this lower bound for monotone real formulas and take it all the way up to the secret sharing schemes. But that was one of the hardest parts of our work. I'll talk about it shortly. The easy part was the upper bounds. So we realized that in the secret sharing schemes, the modern one, which I talked about, with the best share size of 3/2 to the n, in every such schemes, it was based on formulas over slices. Actually, implicitly, these secret sharing schemes started with constructing a formula over slices for any function, and then continued by implementing it for secret sharing. So it was implicit, though not that obvious for all of the works. We did have to work a bit hard to formalize it. And the other part of the upper bound chain is a result by Rosenblum, which says that every slice function has a monotone real circuit for it of linear size. So if we get a formula over slices, we can simply replace every slice gate with a small number of monotone real gates and get this upper bound result. So if we have these transformations, we can go in the other direction and take a lower bound for monotone real circuits all the way back to secret sharing schemes. But this lower bound is not the one we wanted to achieve. This is only 2 to the omega of n to the third, because it's for monotone real circuits. And a major part of our work was understanding that we can actually take the lower bound for formulas and take it back to the secret sharing schemes, because that transformation by Rosenblums that take slice functions and replaces them with monotone real circuits, it actually creates monotone real circuits with a specific structure. And since they have this structure, these circuits are limited, and the lower bound for formulas also applies to them. So that's in summary, the result, I'll go back to the previous slide. So we got new upper bounds for formulas over slices in monotone real circuits, and new lower bounds for formulas over slices and secret sharing schemes for recent techniques that were all based on formulas over slices. And to sum things up, I think we've seen really interesting connections between secret sharing and other monotone complexity models. And the natural questions to follow up from here are, can we find better upper bounds or lower bounds for actually all of these models, since in all of them their results are not tight and everything in between is possible.
Okay, great. Thanks for that. If anyone has questions, I'm monitoring so far, no questions in the chat, but maybe let's wait for a minute. Okay, great. Thanks a lot, Oded.
Okay, thanks.
Maybe we can get Johannes to start sharing. And we'll move to small hazard-free transducers.
Can you see my slides?
Yeah. Yeah, maybe you
Perfect.
can get started as well, Johannes, and then we can do all the questions in the end.
Okay, I'm fine with that. Yeah, thanks for the introduction. I will present small hazard-free transducers, which is joint work with Christoph Lenzen and Moti Medina, which should also be here. I appreciate that. What we look at is the circuit complexity, but not in binary logic, but in ternary logic. And this means that we take the binary logic, we take value 0 and 1, and we extend it by a third logical value. In our case, we call it U because we see it as uncertainty, in the sense that if you're not sure if your input is 0 or 1 or anything, then you replace it by U. This has been introduced by Kleene, and it's been called a three-valued logic before. We call it the ternary logic. The extension to basic gates is fairly natural. So if you take a NOT gate and you get a certain input, 0 or 1, then your output is also certain. And if your input is uncertain, then you don't know. It can be 0, it can be 1. So you also output uncertain output. It gets a little bit more complicated if we look at AND gates or OR gates, because if you have an input that already determines the output, you can output a certain output. So for example, if one of the inputs to your AND gate is 0, then you will always output a 0. But in the other case, if your output is 1, if your input is 1 and the other input is U, then U may be a 0, it might be a 1. You never know, and you never know what your AND gate will evaluate to. So you also output a U. And this leads me basically to the question, what is the most precise output that we can have? How can we define what we actually want to compute with hazard-free circuits? And I get into some technical definitions, or at least I try to convey the idea of what's behind it. So first we have function res, which is for resolution. It takes a string in the ternary world and produces a set of binary strings that represent this ternary string. So it might be all resolutions of the ternary string in the binary world. And then we have the other direction, which we denote by the star operator, which is basically a superposition of binary strings. It takes a set of binary strings and produces the most precise ternary string representing all of these inputs. So to say, this is the string with the longest common subsequence, so to say. And basically what these two enable me or us to do is to define the hazard-free extension of a function. So assume you're given a function in a Boolean world, and it's called f, then we denote its hazard-free extension by fu, and it's defined in the following way. We take the set of all possible resolutions of your input, and we evaluate f on this set, which gives us a set of all possible outputs. And then we take the superposition of all possible outputs. So the hazard-free extension of a function basically represents the most precise output any circuit can have in face of uncertain inputs. Yeah, basically that's also the definition for hazard-free circuits. Any circuit C that implements a function has a hazard if it does not implement the hazard-free extension. Two results that are known on hazard-free circuits, or on the complexity of hazard-free circuits. Well, first of all, every Boolean function has a hazard-free circuit computing it. This has been known for quite some time. But recently, it's been shown that there is an exponential separation between the complexity of Boolean circuits and their hazard-free counterparts. So actually, we can find functions f where the smallest circuit that implements f is exponentially smaller than the smallest circuit implementing the hazard-free function. So, and these two works lead us to the question that we try to answer in this work. Basically, are there functions that have efficient hazard-free implementations? And we answer with, yeah, we can construct efficient circuits for transducer functions. Transducer is basically a Mealy machine, which is defined as this tuple with a set of states. So S is the set of states. We have a starting state, we have an input alphabet and an output alphabet, and transition and output functions. So transducer, or the transcription function of the transducer now is defined by tau, which is the function that takes a string of inputs and produces a string of outputs of the same length. And what we show in our work is how to construct circuits that implement the hazard-free transcription function. So, and these circuits will have size linear in the size of the inputs and depth logarithmic in the size of the inputs. But you see here that actually we might have large constants, so to say, as is the size of the state space, and L is the size of the input alphabet. But we've seen before that there's this exponential separation between hazard-free circuits and their Boolean counterpart. So this basically shows that we cannot get around these large constants. And that's it for now.
Yeah. Quick question, Johannes. So, but is the lower bound from Ickenmeyer et al. As well for transducers as well? Like that separation, or?
No, it applies in general. I'm not sure if we can directly apply it to the transducers or not. Sorry, I would have to look into that again.
Okay, yeah, sounds good.
But in general, we cannot get around
right.
this explanation.
Sounds good. There's one question from Udi. Can you say something about the separation result? Is it a simple function? Is the smaller possibly hazardous polynomial?
Sorry, I didn't get the last part.
Oh, sorry. Yeah. So there's a question in the Q&A. Can you say something about the separation result? I guess he's asking about the separation between from Ik and Maya et al. Is it a simple function that they use for the separation?
I think it's for matrix multiplication. They can show it, and I have to lie, but if I recall correctly, they reduced to monotone circuits and applied the lower bounds from monotone circuits on hazard-free circuits.
Okay, cool.
Yeah. That's it from my side.
Oh, okay, great. So sorry.
Appreciate more questions.
Yeah, no, Oded is thanking you for the question and for the answer.
You're welcome.
Okay, yeah. Do you mind going to the conclusion page? There's another.
No, this is the answer from.
Oh, there's an answer here. Okay, there's another answer by Christoph here. So I'll just read for everybody else that the lower bound applies in the sense that one could set up a state machine that just reads and stores the entire input in its state and then computes an arbitrary function. Oh, okay. So there is a lower bound here as well in your theorem. Is that correct, if I understood, Christoph?
Yeah, I think what Christoph wants to say is we can also find a state machine for every function, which basically reads your complete input, stores it, and then it gives the according output. This will produce a very large state space, and yeah, the state space here appears exponential.
Oh, right, I see. So you also capture kind of the functions that could be lower bounded, right? So therefore, like, this is in a sense kind of incorporates the lower bound. Okay.
Yeah, this is the short answer to your question, yeah, I guess.
Cool, thanks. Any more questions? Okay, there's no more questions. Thanks again, Johannes. So, and now William will tell us about what does dynamic optimality mean in external memory.
All right, thanks. So, okay, yeah, so I'm Bill Kuzmal. This is joint work with Michael Bender and Martin Farach-Colton. And in order to try to make sure there's room for questions, I'm just going to try to give a very brief overview of our paper. What does dynamic optimality mean in external memory? So first of all, what does dynamic optimality mean in internal memory, right? So it's this very old problem. The question is, can you come up with some rotation-based binary search tree that is in some sense the single best search tree in the world? And in particular, you would say that a tree is dynamically optimal if it's constant competitive with every other rotation-based binary search tree on every input. So it's kind of the strongest sense of optimality you could hope for. And this idea was introduced in the 1980s. And what makes it so interesting is we actually think there is such a tree. So Slater and Tarjan introduced the display tree, which is widely believed to be dynamically optimal. And although we don't know whether the display tree is dynamically optimal, we do have a whole bunch of interesting results in this area. So for example, Demain et al. Showed that the Tango tree is within a log n factor of dynamically optimal. That's classical dynamic optimality, and there's a whole bunch of other interesting results there. But what I want to talk about today is a direction that researchers have started to consider in the last 10 or 15 years, which is, if that's dynamic optimality in internal memory, what should it mean in external memory, in the external memory model? So here, of course, the classic data structure that you use for your search tree is the B tree, introduced in the 1970s. But the focus that we're going to be really taking today is on an interesting feature of the external memory model, which is that even though the B tree is a classic data structure, it's actually not the only tree in town. And let me tell you what I mean. So it turns out one of the peculiarities of the external memory model is that there's actually two parameter regimes for search trees. So maybe the regime we're most used to thinking about is the query heavy regime. Most of the operations being performed on your tree are queries. And in this regime, B trees are optimal. And in fact, there's been a whole bunch of interesting work on what should dynamic optimality mean for B trees. This turns out to actually be itself a pretty subtle question, because you have to figure out what's the class of data structures you want to achieve optimality against. On the other hand, what's interesting about external memory is that there's also this other regime, the modification heavy workload regime. So this is the regime where you have lots of insertions, updates, and deletions occurring on your tree. And here, B trees actually aren't optimal. In fact, you can actually implement your insertions, updates, and deletions to be sub-constant amortized time. And so that's the setting that we're interested in this paper, is we wanted to ask the question, what should dynamic optimality mean in this setting, in the modification heavy setting? So I'm just going to briefly summarize kind of the big picture of what we do in this paper, and I'll be a little bit informal, but I'm happy to, talk about any of these in more detail if anyone's interested. So the first contribution of this paper is really a modeling contribution. How should we define dynamic optimality in this setting? And so the first thing we do is we define the notion of a buffer propagation tree. It's a class of data structures that includes kind of the classical data structures for the modification heavy setting, but it also captures the various ways in which you could adapt your data structure to the specific properties of a workload. For example, taking advantage of the fact that there's going to be lots of insertions to one part of a tree, but maybe lots of queries to another part of the tree. So we define the class of buffer propagation trees, and we formalize the question of, can you achieve dynamic optimality against them? Our second contribution is we introduce a new data structure that we call the Jello tree. And the Jello tree isn't dynamically optimal, but it does have an interesting feature that it's statically optimal in this model. So the Jello tree is constant competitive with any buffer propagation tree, with the restriction that that buffer propagation tree has to pick its structure up front, and it can't change its structure afterwards. Of course, this raises the question of, well, can we argue that somehow the Jello tree maybe isn't fully dynamically optimal, but has some sort of weak notion of dynamic optimality? And this brings me to the final contribution in the paper, which is we show that the Jello tree is constant competitive with any buffer propagation tree that is what we call speed limited. So this means that the opponent, the adversary, buffer propagation tree, doesn't have to be static, but instead it has this restriction, which is that it's only allowed to spend some limited fraction of its IOs on restructuring, on changing the shape of the tree. And so we show that if a buffer propagation, if we're talking about sufficiently speed limited buffer propagation trees, then our Jello tree is as good as that. And this is interesting because it kind of gives a continuum between static and dynamic optimality. So we're not optimal on any input sequence, but we would be optimal on any input sequence that has the property that the optimal tree for that input sequence only changes slowly over time. And this is a notion of this kind of continuum between static and dynamic optimality. You could actually also define it in internal memory. And that's one of the big questions that we were left wondering at the end of this paper is maybe there's something interesting you could say about, for example, splay trees in this speed limited setting. And we don't know the answer to that question. Okay, so that's a brief overview of the results in this paper, just in kind of an informal statement of each of them. And one other open problem I just want to leave you with is that the Jello tree data structure and its analysis is actually pretty involved. it's a pretty complicated analysis. So another open problem that I think is interesting is just, can you come up with a simpler way to achieve these kinds of results in this model? Or do you really need the full muscle of the Jello tree? Okay, that's my summary of the results, and I'd be, very happy to answer any questions.
Okay, great. Thanks, William. Okay, if anyone has a question, you can chat at that type or raise your hand, and I can also figure out if I can unmute you. Apparently I can. Okay, so there's one question here from Eric. Sorry, what was the speed limit constraint for internal memory? A sublinear number of modifications?
Good, that's great. So yeah, so here's what I'm kind of imagining for internal memory. So first of all, in external memory, it's kind of the same situation where we're requiring it to make modifications at almost an unfairly slow rate. So imagine you say, okay, you have a display tree is allowed to do what display tree does. It's not limited, but opt, which is your adversary, is constrained so that it can only, for example, do epsilon rotations per tree, an average of, some number of rotations per, either it's epsilon log n rotations per tree insertion, or maybe even just epsilon rotations per tree insertion. Sorry, not tree insertion, per query in the tree. And then the natural question is, if you assume that epsilon is small enough, can you say something about being within a constant factor of dynamic optimality? I don't know, does that make sense?
Okay, let's see what Eric says. Eric, I think you're allowed to talk if you would like.
Yeah, that sounds good. So you're imagining epsilon is a constant in particular, or maybe even less than 1.
Yeah, even subconstant possibly. Yeah, like asymptotically subconstant.
Interesting. Yeah, it's a cool question.
Okay, do we have any more questions? Okay, if not, let's thank William again. Well, I'll thank for everybody. And okay, so now we'll have Samia Brata talking to us about support recovery in universal 1-bit compressed sensing.
Hello, everyone. Can you see my slides?
Yes, yes.
Hey, everyone. So my name is Pal.
What can I do for you?
Sorry.
It's all good.
Sorry, for some reason, Siri has been speaking on my behalf.
It's okay, it's okay.
And I don't know how to put it off. Okay, I think I stopped. So hey everyone, my name is Shomabruta Pal. I'm a postdoc at Google Research, and today I'll be talking about support recovery in universal 1-bit compressed sensing, which is a joint work with my PhD advisor, Arya Mazumdar. So in the present world, data is ubiquitous, it is everywhere, and it's important to store and reconstruct it efficiently. And it is a significant challenge to store the large amounts of data without some kind of structural assumptions. And the most natural structural assumption, which in practice is true, luckily for us, is that most signals such as audio and images are sparse in some domain. So if you do a Fourier transform of images, it can be represented as a sparse vector, which means that it has only a few non-zero entries. So let me give an example. that although most images which are, which are arbitrarily created, look random and are hard to compress, for example, these images, most images that we care about are highly structured. And since they are structured, it can be transformed via some Fourier transform or wavelet transform so that it can be represented as a vector with only a few non-zero entries. Okay, so let's assume that this change of basis has been pre-applied to make the data sparse. So let's be a bit more mathematically rigorous. So the signals that we care about can be represented as a vector in, say, n dimensions. And the important thing is that we know that this vector is sparse. The signal is sparse. That is, it has at most k non-zero entries. Okay, and we will call the set of non-zero indices of x or the vector to be the support of x. Now, interestingly, it can be shown that such sparse signals can be compressed and reconstructed by using quantized linear measurements, where the number of measurements is much smaller than the latent dimensionality, which is n. Okay, and we can do this by using the structure that is the sparsity crucially. So let us look at an extreme quantization setting, which is known as the 1-bit compressed sensing setting. And in this setting, what we do is we compress a signal by using the signs of the inner products with the signal. Okay, so let me give just a few more details to introduce the problem. So suppose sine is a function which takes a real number as input and returns 1 if the input is positive, 0 if the input is 0, and -1 if the input is negative. And we can extend this notation to a vector, which means that sign of a vector is the sign of each entry of the vector. Okay, so now what we have is the following. We have a measurement matrix, let's call it A, which has some number of rows, where the number of rows is much smaller than the number of dimensions. That is, we make some measurements where the number of measurements is much smaller than the dimensionality n. Now, what we get to observe is the sign of this measurement matrix times the signal vector. Okay, and our goal is to reconstruct the signal vector from this observed and from these observations. So in the reconstruction problem, what we have is the following. We have a known measurement matrix A. We have an unknown signal vector x, which is of dimension n. And we have an observed vector y, where every entry is +1, -1, or 0, since y is just a sign of A and the unknown signal x. Okay, and our goal is to recover this unknown signal x from this observed vector y. Now, this problem has applications in many domains, such as photography, holography, and facial recognition. And an important property that we care about is the following. The measurement matrix that we choose must work for all n-dimensional signals, which is k-sparse, that is only have a few non-zero entries. And this is important in photography because we want a single algorithm to work for all images that we take through the camera. Okay. And our objectives can be twofold. First of all, we can go after signal reconstruction, where we want to reconstruct the entire unknown signal x, or we can, the other goal is to recover the support. That is, we only want to recover the indices of the non-zero entries of the unknown signal. And there are several possible notions of support recovery. We can recover the exact support from the observations, which is also called the universal exact support recovery. Now, again, let me reiterate that the measurement matrix A that we design must work for all high dimensional signals with sparsity at most k. Okay. So suppose now that we are okay with making a few mistakes, we do not need to return the exact support. So we can define two other notions of support recovery in that context. So suppose we can make we can return a set which has a small number of false positives and a small number of false negatives. That is, suppose it is okay if we insert a small number of indices which are not within the support in our final answer, or we omit a few correct indices of the support in the final answer. So this is what we call an universal approximate support recovery. And this epsilon denotes the number of mistakes that we're allowed to make. The other notion is universal superset support recovery. And here we are only allowed to make false positives. That is, we want to return a set which is a superset of the support of the unknown signal. We are not allowed to omit any index from the support of the unknown signal vector. Okay. And let me briefly discuss our results. So for exact support recovery, Acharya et al. Already showed that O of k square log n measurements are sufficient to design a universal measurement matrix that can recover the support of all k-sparse signal vectors. Exactly. Okay. So basically for exact support recovery, O of k square log n measurements are sufficient, and this bound is nearly tight. And for binary signals, when it is known that the unknown signal vector is binary, the k square term can be improved to k to the power 3/2. Okay. So for approximate support recovery, here, if you look at this result, just treat epsilon as a constant. We can show that O of k log n measurements are sufficient for approximately recovering the support of any unknown signal vector. So here we can improve the index here we can improve the dependency on k from k squared to k when we go from exact support recovery to approximate support recovery. And we can again show that this bound is also tight. Next, if we move on to superset recovery, it turns out that O of k to the power 3/2 log n measurements are sufficient. So this is an interesting open problem. Can we close the gap between the sufficient number of measurements for superset recovery? The current upper bound on the number of measurements is k to the power 3/2, and the current lower bound on the number of measurements is O of k. So there is a k to the power half gap between the upper and lower bound. And it would be very interesting if it is possible to close it in some future work. So we can provide other results as well if we have more structural assumptions on the unknown signal vector, and you can refer to it in our paper. So before ending, let me just give a brief parallel with another problem called group testing. So many of you, I think, are already aware of this problem. Here, instead of, this problem is very similar with the 1-bit compressed sensing setting, but here the unknown signal is binary. The measurement matrix is also binary, and the operation between the measurement matrix and unknown signal vector is not linear, but it's a logical OR operation. Okay. So because of this operation, what we do observe is a binary vector, okay, which is y having m entries, and our goal is again the same, to recover the support of the unknown signal. Now, although this problem has many parallels with 1-bit compressed sensing, the crucial thing in group testing is that an observation of 0 means that all the indices of signal in the support of that measurement is 0. And this property can be crucially used to provide results for all these notions of support recovery that are tight. Okay? But for our problem, these techniques could not be extended, and require several new ideas. And this is where I think I will end.
Okay, thanks very much, Umberto. All right, does anybody else have questions? Okay, in this case, let me just see if there's something in the Q&A. No. Okay, so in that case, I'll thank the speaker again. And all right, I'll thank all the speakers in the session. So thanks for the great talks. And yeah, we're all ready to go. Okay, bye-bye.